How many oscillations was 9.11 seconds?
10.
Yeah. The period is 0.911, which makes this 6.897. So point, both, which I had to erase that number so quickly.
.0436.
0.0436. All right, units?
Kilogram.
Yeah. That was the clue that somewhere I messed up. Because I feel pretty confident that the effective mass of that slinky is not 4 kilograms. All right, so we now have an effective mass of the slinky itself. So we can add this, in essence, 43.6 grams to anything that we attach to it, and we can make predictions about what the period is, as well as omega, and then we can confirm that through various means here. So let's add a 50 gram mass. Actually, I'm going to add let's see what 220s does. Fortunately, the amplitude is of no concern here. Let's see what it will pick up. All right, so let's make a prediction. We have 40 grams added to it. So the period should be two pi over omega, which is 2 pi times the square root of math m over k, which is 2 pi times the square root of our mass, which is 0.04, what I have added over there, plus the effective mass, 0.0436, divided by our k value, which is 2.07328.
I got 1.263. Same.
Same. Units?
Second.
Yeah, it's period. Also, this is newtons per meter, and a newton's got a kilogram meter per second squared, so that kilogram will cancel out with kilogram built in there. The meters will cancel out, what you're left with is square root of second squared. All right, so we have a couple of predictions here. We have a period, omega. Well, we'll check omega in just a second. All right, we're going to do 10 oscillations. And to make sure that this is going to run for enough time. Let's see, duration. So 10 oscillations should take 12 seconds. So let's do 20. All right, 2, come on, 1, try that again, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is just garbage. Yeah, let's figure that. It's picking up these. What'd you get?
12.15. I got 12.39.
So 12.39 and 12.15.
15.
Not too far off. So it's a difference of 24, so 12 points. No. Yes, it is 24, so 12.27 seconds, or actually 1.227 seconds. Where's our prediction of 1.263? Not too bad. However, what I was hoping was that we could get omega here. All right, so looking at the display, it was doing the classic oscillation, which is what I would expect, but then suddenly it missed everything and shot up to 3 meters. So what I'm gonna do is highlight a section that excludes that.
If you highlighted the whole section, including that, would it still throw it off a lot?
Yeah, I would think so, but you know, we'll check that in just a second. So analyze curve fit position. I want to do a cosine curve. And I'm assuming that you can see this incredibly well because you're young and you have better eyes than I've got. Can you?
Not me.
Can you?
Not really.
There's a red line and a black line. The red line is the actual position,
Okay.
and so the red line is the actual position and the black line is the curve fit. And you can see there should be brackets. Oh no, I zoomed in on that. So we have B is our omega value. So we have 5.14 as omega. I don't think this one's gonna work as well. But we'll see. So omega is, what did I just say, 5.14?
Sounds right, but yeah.
And that should be equal to the square root of K over M, which is the square root of 2.07328 over, and probably would be faster to use this one, but over 0.0836, which is the combined effective mass plus what I added. So it's experimental.
I got 4.979.
All right. 4.979?
Yeah.
I hope you got something similar. You got something very different?
Tell you in a second.
Did you get 5.14 exactly?
4.98.
Okay. Again, not too far off of what the experimental value was. And then to answer the other question of if, oh, and then for the camera, although that'll probably come in blurry, if it could be seen at all, cancel, graph, zoom out, analyze, curve fit, position, cosine, and it got, looking at the whole thing without narrowing down, 11.2 as the value for omega.
So, yes, it really throws it off.
Yeah.
What does the graph look like? Did it treat the
It's hard to
crazy data as a peak?
It didn't, but it affected the shift. That's hard to tell what exactly is.
Oh.
Actually, so if I hit click OK, it should be graphed there. Now, if I highlight this graph, zoom in, then you can see that it's off.
Yeah.
But fortunately, you would see that and you go, wait, something's off. 110 students look at that and go, well, let's just write the numbers out. Sorry, I was grading 110 labs earlier today, and there was just some stuff that was just clearly off. That it would have been nice if a red flag had gone off. So if you're a 110 student watching this, please take better care. All right, questions on this? All right, the lab you're doing Wednesday is going to be similar to this. More thorough, you aren't trusting the manufacturers. All right, what we're gonna do now is we're gonna head out to the hallway because I need a place without a carpet. And I need this rod. And I may as well pause this. All right, so when you're dealing with the harmonics, you have to sort of figure out what are the standing waves. And to figure out the standing waves, you need to figure out where the nodes and antinodes are. So if I have a situation where I've got, let's say this water tube right here. If I send the sound wave down into it, it's gonna hit some surface. When we put water in there, it'll hit some water surface and the wave will bounce back. Up here, we have completely open end. So what, in terminology we've used before, that would be a fixed end down there and a free end up here. Well, when you're dealing with harmonics, a fixed end is a node, and a free end is an antinode. So we've dealt with the two fixed ends, now let's deal with one fixed, one free end. And the simplest wave you can produce with one fixed and one free end would be, I'll go vertical on this one. That would be the simplest harmonic. This is the first harmonic. And how many waves is that? Let's take a look, come back to it. With two fixed ends. The simplest harmonic is that. The next simplest harmonic, so that's the first harmonic. That's the next simplest one. the second harmonic. Third harmonic, and so forth, stuff that you saw in lab last week. Well, if you think about a sine wave, when you draw a sine wave, how far do you usually draw it?
One period.
Okay? Which of these would be one period?
Second harmonic.
Yeah. So if that is one wave right there, or one wavelength, how many wavelengths is that?
1/2.
Not a half.
Or
So going from node to the first antinode.
fourth.
Yeah. That's a quarter of a wave. So if this length, if that length there is L, L is equal to 1/4 of a wavelength. Where the wavelength of it would be 4 times L. So it's like a 2 there. The next simplest. This is the third harmonic. How many waves is that?
3/4.
Yep. So the wavelength is 4/3. The next harmonic is the fifth harmonic. That is really badly drawn, but I'm assuming in your notes or in your mind, it is done perfectly. How many waves is that?
5/4.
Over here, how many waves is this?
1/2.
So the wavelength is 2L. How many waves is this?
1.
How many waves is that?
3/2.
Notice that once you have the first one set up, you're adding a half wave every time. This is one wave, one wavelength, 2 wavelengths, 3 wavelengths. First, second, third harmonic. Over here, we have 1/4, 4, 1/4, 3/4, 5/4, first, third, fifth harmonic. I don't know what the second harmonic would look like if it existed. But in both cases, you add a half wave every time. And the third case, when we have 2 free ends, we'll also be adding half a wave. All right, so what would this sound like? If this is, remember we're dealing with sound, if we were dealing with sound, which we will be, this would be an indication of pressure, high pressure, low pressure, atmospheric pressure, or ambient pressure. If air pressure is oscillating the most, how would we sense that if we're dealing with sound?
You said if air pressure was oscillating the most,
What is oscillating the most?
the higher pitch
Not
sound.
higher pitch,
The loudest,
louder.
the fundamental or whatever.
So, let's see what happens here. So first thing I'm gonna do is I need to put water into the tube. Now, putting water straight into here, probably gonna make a mess, so we have a reservoir here. And assuming there's no kink, water's rising up in the tube and it's gonna come up until it's even with the water on the other side. And if air pressure on both sides is the same, air pressure here and air pressure here is the same, the water should level out. All right, water's still rising. I don't know if you can see it, but the water's here at this point, and it is leaking. Oh, it's leaking from the middle of it. Where? Oh, bugger. It's leaking from up here. I'll be back. I'm just gonna let the recording go.